Hello, everyone. Welcome to the lecture on Chapter 5, and in particular, I want to focus on sections 5.1 and 5.2 in this video. Okay, so Chapter 5 is on exponents and polynomials. And the first section, 5.1, is on the different laws or rules for exponents. So laws of exponents. So there's several rules that you need to learn before we start talking about polynomials in general. So if I have a power, right? If I have, say, 6 raised to the 4th power, the 6 here is called the base, and the 4 is the exponent. And we know what this means, right? This means 6 times 6 times 6 times 6, right? There's 4 factors of 6. I multiply 6 4 times, right? So in general, if we have, say, x to the a, where a is a positive integer, then this is equivalent to saying x times x times x dot 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 x. And how many x's are there? There's a x's, right? So there's a factors of x. So like in the example above, the x would be the 6 and the 4 would be the a. So there would be 4 6's, right? 4 x's. And again, this is true if where a is a positive integer. Okay, so here's the first rule for exponents. Different books call this different things. In this book, they call it the exponent 1 rule. And all it says is that for any real number x, if I raise x to the 1 power, so if my exponent is a 1, that's just the same as x. And usually we never even write the 1, right? We assume that there's a 1 there. There's an implied 1 there. So x to the 1 is just simply x. Okay, there's a similar rule. It's called the exponent 0 rule. And what this says is for any non-zero real number x, so we have to strict it. X can't be 0, but it can be anything else. If I take that x and I raise it to the 0 power, so if my exponent is a 0 now, that's always by definition equal to 1. Okay, so some examples would be the following. Like if I had, negative 2/3 to the 0, that's 1. Or if I had, xy squared, as long as x and y are not 0, so if they're anything else and I raise it to 0 power, that's 1. Or if I have, well, let's do the other rule too. Let's say I have x squared y cubed raised to the 1. So now it's to the 1 power. Well, this just stays the same, right? This is just x squared y cubed. So if you raise it to the 1 power, if the exponent is a 1, then it stays the same. If you raise it to the 0 power, then the answer is equal to 1 by definition. And you'll see later when we talk about dividing powers why that makes sense. Okay, another rule is something called the power rule. Or sorry, product rule. So product rule, we'll do that one first. So product rule of exponents. So what this says, for any non-zero number x, and for any integers a and b, if I multiply x to the a times x to the b, so if I have two powers and the bases are the same, right? They're both x's in this case, right? So same base. What you do to get the result is you keep the base, so it's still x, and you add the exponents. So the rule is a plus b. You add the exponents. Okay? So let me do a couple examples. Let's say we have, x to the third times x to the fifth. So the bases are the same, so I keep the base. And then I add the exponents. Well, what's 3 plus 5? That's equal to 8. So this answer would be x to the 8th. If I had, z to the negative 4 times z to the 9th, then this would be z, and I have to add negative 4 plus 9, but we know that's 5, so this would be z to the 5th. Okay, if I had, I'll do a couple more. Let's say I have negative 7 squared times negative 7 cubed. Well, that's going to be negative 7 to the 2 plus 3, but that's just the 5th. Okay, so you keep the base, right? If the base is the same, you keep the base and you add the exponents. So that's the product rule for exponents. There's something similar for when you divide. It's called the quotient rule. And what this says is for any non-zero real number x, and for any integers a and b, if I divide two powers, right? So if I have x to the a divided by x to the b, and the bases are the same, so the x's are the same, then the result is you keep the base and you subtract the exponents. So it would be x to the a minus b. You would subtract the exponents. So a few examples of that would be the following. Let's say we have 8 to the 11th over 8 to the 3rd. Well, I have the same base, right? 8, so I keep the 8. And then I would do 11 minus 3, but that's equal to, in this case, happens to be 8. So the answer would be 8 to the 8th. And you could expand it out, right? It'd be 8 times 8 times 8 times 8, 8 times, some really big number. I'll just leave it as 8 to the 8th. Okay, what if we have z to the fourth divided by z to the negative 3? Well, again, I have the same base, so I keep that base, z, and I would subtract the exponent. So 4 minus a negative 3 is the same thing as 4 plus 3, so this would be z to the 7th. Okay, if I had, say, m to the 20th divided by m. Well, you can think of that as m to the 20th divided by m to the 1, right? So I keep the base, and I would subtract the exponents, but then that is equal to m to the 19th. Okay? What if I have x to the 7th divided by x cubed? Well, this is going to be x, and then it'll be 7 minus 3, so it'll be x to the 4th. Can you guys see why this works? Like, if you think about it, x to the 7th, I could write as x just multiplied by itself 7 times, right? So 4, 5, 6, 7. And then x to the 3rd is x multiplied by itself 3 times. But look what could happen, right? I can cancel 3 of these, right? They're just equal to 1, x over x, x over x, x over x. And I'm left with just x to the 4th in the numerator. But the rule that will get you that correct answer is you subtract the exponents. Okay, what if I have x to the 5th divided by x to the 5th? Well, okay, so it's x, and the rule is I subtract the exponents, so 5 minus 5, but that's x to the 0, and what is x to the 0 by definition? That's equal to 1. And actually, this makes sense, because if I had something x to the 5th over itself, couldn't I just cancel these and say that's equal to 1, right? It's a factor of 1. Anything over itself is equal to 1. So that's why that rule, anything raised to the 0 power, has to give you 1, because it has to fit logically. Okay, another rule is, what if you have a negative exponent? So negative exponents. So for any non-zero real number x, and for any integer a, the following is true. If I have x to the negative a, that's the same thing as 1 over x to the positive a. So I can put the x, the power, down into the denominator, but it changes the sign of the exponent. Or you could go the other way too, right? Or if I had 1 over x to the negative a, I can bring that power up to the numerator as long as I change the sign on the exponent. So that becomes x to the a. So some examples are things like this. If I had, let's say I had 3 to the negative 2. Well, this is the same thing as 1 over 3 to the positive 2, right? I have to change that exponent to a positive 2. And then what's 3 times 3, right? 3 squared means 3 times 3. That's just 1 over 9. So that's really, 3 to the negative 2 is the same as 1/9. If I had, say, q to the negative 12, well, I could rewrite this as 1 over q to to the positive 12th. If I had, say, negative 7y to the negative 1, then you have to be a little careful here. So the negative out front stays, right? That's not part of the power. And then what this says is this is the same as 1 over 7y to the positive 1. But remember, what's 7y to the positive 1? That's just 7y. So this would be negative 1 over 7y. Let's say I had negative 5, and the whole thing is now being raised to the negative 2 power. Well, this is the same as 1 over negative 5 raised to the second power. And now since the entire thing, right, the exponent, the 2 is acting on the entire negative 5, then this is really the same as negative 5 times negative 5, and that's a positive 25. So negative 5 raised to negative 2 is a positive 1 over 25. Okay, a few more examples with this. Let's say I had 7 over x to negative 3. And let's say I didn't want to write this with any negative exponents. Often when they have you simplify these expressions, they want the answer to have just positive exponents at the end. So what I could do is I could write this as, well, this is the same as 7 times 1 over x to the negative 3. But remember, the rule is I can take this, and if I bring that power to the numerator, it changes that exponent, right? It changes the sign. So in this case, it'll become positive 3. So 7 over x to the negative 3 is the same as 7 times x to the positive 3. The other way of thinking about it is if you take this x to the negative 3 and you move it to the numerator, it's going to change the sign of the exponent. Okay, a few more examples. Let's say we have a to the 4th over b to the negative 2. Well, I could write this without any exponent or without any negative exponents. So the a to the 4th is fine, so I can keep that in the numerator. And I can bring the b up into the numerator, but I have to change that sign to a positive 2. So that would be the answer. A to the 4th times b to the positive 2. And then let's say I have 1 over 7 z to the minus 3. So the 7 is fine. I can leave that in a denominator. But then the z to the negative 3, and the negative 3 only acts on the z, right? If the entire 7z were in parentheses, it would act on the entire thing. But in this case, it's only acting on the z. So I could bring the z from the denominator to the numerator as long as I change the exponent, change the sign on it, so it becomes positive. And of course, this is just now, you could write it as z cubed over 7. Okay, so that's how you deal with negative exponents. When they move from the numerator to the denominator or denominator to numerator, their signs change. Okay, so that was it for 5.1. 5.2 is going to give you more rules, more laws for exponents, and we're also going to talk about something called scientific notation. Okay, so let's do 5.2. So I'll say more laws, components. And we'll also talk about scientific notation. Okay, so another rule is something called the power rule of exponents. So what this says is for any non-zero real number x, and any integers a and b, if I take a power, say like x to the a, and I raise it to another power to b, then the rule is I can simplify this just by keeping the base there and then multiplying the powers. So x to the a all raised to the b is equivalent to x to the a times b. Okay, here's an example. Let's say I have x squared, and I'm going to take that whole thing and raise it to the fourth power. Right? So if we were to write this out, remember x squared to the fourth means x squared times x squared times x squared times x squared, right? It means multiply it out 4 times. But then you could say, well, x squared means x times x. So this is going to be another x times x, then x times x, and then x times x. So how many together do I have? I have 8 of them, so this is x to the 8th. But the quick way of doing that is to say, well, this must be equal to x, and then if I multiply the 2 times 4, I'm going to get my 8. Okay, but that's why it works. If you expand the whole thing out, you'll see that it's the same thing as x to the 8th. Okay, let's do a few more examples of this. Let's say we have negative p cubed raised to the 5th. So the negative stays, right, because that's outside of the parentheses. And now what's p cubed raised to the 5th? Well, remember the rule is I would do p, and I have to multiply 3 times 5. So this is going to be negative p to the 15th. Okay, what if I have 2 to the negative 4 squared? Well, the rule is keep that base 2, and I multiply the exponent. So what's negative 4 times 2? Well, that's going to be a negative 8. And then we can use our other rule. We could say, well, this is the same as 1 over 2 to the 8th, right? If I bring it down into the denominator, you can think of it as there always is a 1 there, so you can leave the 1 in the numerator. If I bring the 2 to the negative 8th down into the denominator, I have to change the sign on the exponent. And if you want, you can multiply this out. 2 times 2 times 2. If you multiply the 8 times, you're going to get 1 over 256. 2 to the 8th is the same as 256. And then let's say I have y cubed raised to the negative 1. Well, this is the same as y to the 3 times negative 1, right, which is y to the negative 3. But then I could rewrite that as 1 over y cubed. So again, the y would move down to the denominator, and I'd have to change the sign on the exponent. Okay, a few more rules. Once you know these rules, then it does make doing these problems much, much easier. So the most difficult part of Chapter 5 is just getting a grasp of all these rules. But once you know these rules, it becomes second nature. Okay, so here's the next rule. Raising a product to a power. So for any non-zero real numbers x and y and any integer a then the following rule is true. If I multiply two things together, say x times y, and I raise that entire product to some power, so my exponent, say a in this case, then we can break this up and we can say this is the same as taking each factor, each piece, and raising it to a, and then multiplying those together. So x times y, all raised to the a, is the same thing as x to the a times y to the a, right? So it's raising a product to a power. That's the rule. In this case, I'm doing it with two factors, but it can be any number of factors. So if I had, say, like, x times y times z times w raised to the a, then this would just be x to the a times y to the a times z to the a times w to the a. So it extends no matter how many factors you have. Okay, so some examples. Let's say I had 2y to the fifth, right? And I want to expand this out. Well, there's a couple ways you could do this, but this is probably the easiest way to do it, is just to use this rule, right? Raising a product to a power. So I could say, well, this is the same as 2 to the fifth times y to the fifth, right? I'm just using this rule right here, right? The 2 is like my x, the y is my y, and the a is like my 5. So this is the same as 2 to the fifth times y to the fifth. And 2 to the fifth, we know we can expand it out. That's simply 2 times 2, which is 4, times 2, which is 8, times 2, 16, and I need one more 2, times 2 is 32. So this is 32 y to the fifth. Let's see, if I had, say, negative 5t to the negative 3. Well, here's one way we could handle this. We could say, okay, the negative just stays out front, right? We can't touch that yet. You can think of it as negative 1 if you want. And then each piece, since we have a product raised to the power, I can raise each piece. So the 5 gets raised to negative 3, and the t gets raised to negative 3. But then we can use the rule that if we have a negative exponent, we can stick the power, we can move it right from the numerator to the denominator as long as we change the sign on the exponent. So the negative 1 will stay. I'll just leave that in the numerator. And then in the denominator, I'm going to get 5, but because I'm bringing it down, this has to change to a positive 3. And then in t, same thing. It'll change to a positive 3. So that would be the answer. And then you could expand out the 5 cubed if you want. Right? It turns out 5 cubed is 5 times 5 times 5, which is 125. So you could write this as 125 t cubed. That would all be in the denominator. Okay, a few more examples of this. Let's say I have this. 4 times x squared y cubed squared. Okay, so now actually we're going to use a couple rules now, right? So the 4 stays there. Here I'm going to use raising a product to a power rule. So the x squared has to be raised to the second power, and then the y cubed has to be raised to the second power. Right, so I'm just using that rule. Remember, if I have x, y to the a, this is x to the a times y to the a. So in this case, my x is like x squared, and my y is like y cubed. Right, so each one gets raised to the second power. And then I can use the power rule, right, where I'm raising x squared to a power. So what do I do with the exponents? I multiply them together. So what's 2 times 2? That would be 4. And then y, I have, it's y cubed raised to the second power, so 3 times 2 is 6. So that would be the answer. It'd be 4x to the 4th, y to the 6th. All right, what if I have this? 3, a to the negative 3, c to the 8th, squared. And I want to simplify this, and I want to write the final answer so that there's no negative exponents. Okay? So first thing I'm going to do is use the raising a product to a power rule. Each thing inside has got to be raised to the second power, right? So I could say 3 squared times a to the negative 3 squared times c to the 8 squared. Okay, now I can use the power rule, right? First of all, 3 squared is just 9, so I can work that one out. And then if I have a to the negative 3 raised to the second power, I can write that as a to the negative 3 times 2. Remember, I multiply the exponent, so that's negative 6. And then c to the 8 times 2, which is 16. And then finally, since I don't want any negative exponents, the 9 and the c to the 16 are fine. I can leave those in the numerator. And then I would put the a in the denominator, and that's okay as long as I change the exponent from a negative 6 to a positive 6. And then that would be my answer. So now I have an answer with no negative exponents. Okay, and then, so that was raising a product to a power. Now, of course, we can talk about raising a quotient, right, to a power. So what this says is for any non-zero numbers x and y, and any integer a, then if I have a quotient, so if I divide two things like x divided by y, and I raise the whole thing, that whole quotient to a, then this is the same as I can break it up and you say, well, it's just the numerator raised to a divided by the denominator raised to a. So that's the rule. Raising a quotient to a power is the same thing as raising the numerator to that power divided by raising the denominator to that power. Sometimes you'll find that that power is negative. So let's talk about that one and I'll give you some examples of this. So the other possibility is that you have raising a quotient to a negative power. So for any non-zero real numbers x and y and any integer a, then if I have x divided by y, so I have my quotient, and let's say I raise it to a negative a, it turns out I can make that negative a positive a if I flip the quotient that's inside the parentheses. So this is equal to y over x to the positive a. So sometimes you may want to just get rid of that negative exponent right in the beginning if you flip the quotient inside. If you flip that fraction inside, then you can change the sign of the exponent and make it positive. Okay? Where does that come from? Actually, here, let's show like why that's true. So we can show it from our previous rules. So let's do a little proof of that. So if I'm starting with x over y to the negative a. But remember, from the rule with the negative exponents, I can write this as 1 over x over y to the positive a. And then using a quotient raised to a power rule, I can write this as 1 over x to the a divided by y to the a. But then remember, you can think of this as a fraction. Think of 1 as 1 divided by another fraction. So x over a divided by y to the a. And remember, how do we divide fractions? It's the first fraction, right, the dividend, times the reciprocal of the second one, the reciprocal of the divisor. So I have to flip that second one. So this is just y to the a over x to the a. And then I can use that quotient, raising a quotient to a power. I can use that rule backwards now, and I can write this as, well, this is now y over x to the a, right? I'm going from here to here now. So what I proved was, remember we started with x over y to the negative a, and we used all of our rules, and we end up with y over x to the positive a, and that's what we wanted to prove, right? So you just end up flipping the fraction inside, and you change the sign of the exponent. Okay, so sometimes that's useful to do if you have a negative exponent right off the bat. All right, so what are some examples of this? Let's start with the regular raising a quotient to a power rule. Let's say if we have x over 4 squared. Well, I can write this as x squared over 4 squared. X squared is just x squared. I can't do anything else with that. 4 squared, if I want, I could write it as 4 times 4, which is 16. So that's x squared over 16. If I have, say, let's say I have negative x squared over y cubed to the 4th. If you want, you can think of this as a negative 1, right, times x squared over y cubed to the 4th. And now I'm going to use my raising a quotient to a power rule. That means that the numerator has to be raised to the 4th power, and then the denominator would have to be raised to the 4th power. Okay, then we can use, so I'm using all my rules now. Since I'm multiplying two things in the numerator, right, and I'm raising it to the 4th power, I can use my raising a product to a power rule. So this is the same as the negative 1 gets raised to the 4th, and then the x squared gets raised to the 4th. And here I still have y cubed to the 4th. But remember what negative 1 to the 4th is, right? Negative 1, I'll do it over here on the side, to the 4th means negative 1 times negative 1 times negative 1 times negative 1. This is just going to be a positive 1, right? Because a negative times negative is positive, times a negative is negative, but then times another negative is positive. In fact, if you raise negative 1 to an even power, like a 4 here, so this is even, then you're always going to get a positive 1. If I were to raise it to an odd, like say 3 or something, then my answer would be a negative 1. So in this case, it's even, so that's going to be your answer, going to be positive 1. So that's just 1, so that's not going to change anything. And then how do I handle the rest of it? Well, I have to use that other rule, raising a power, right? Or a power to another power. So I multiply the exponents. So this would be x to the 2 times 4, which is 8. And then y to the 3 times 4, which is 12. And that would be my answer. So this original problem here, negative x squared over y cubed to the 4th, ends up being just x to the 8th over y to the 12th when we use all of our rules and expand it out. Okay. Let's see. Oh, a couple more, and then we'll talk about scientific notation. We're only going to do a little bit on scientific notation. What if I have b over 3 to the negative 1? Well, now I could use that rule where I raise a quotient to a negative exponent. And remember, the rule is you flip the fraction, and then you can change the sign on the exponent. So a negative 1 becomes a positive 1. But then, what is anything raised to the positive 1 power? It's just itself. So this is just 3 over b, right? And we're done. Okay, and then the last one, this one's a little more complicated, but if you can do this one, you can do any of these. So let's say I have q to the 5th over 5p to the 4th, and it's raised to the negative 2 power. Okay, so since I have a quotient raised to a negative power, I'm going to use that rule where I flip the quotient inside. And then what does that do? It changes that negative 2 to a positive 2, right? Then I can use the rule, well, if I have a quotient to a power, that means that the numerator gets raised, the entire numerator, right? So you gotta be careful. The entire numerator gets raised to that power, and then the denominator also gets raised to that power. So I'm using that rule. Then I'm going to use the rule in the numerator there where I have a product raised to a power. So that means the first thing gets raised to the 2, and then the second thing would also get raised to the 2, so it's also squared. And then I still in the bottom I have q to the 5th squared. Well, 5 squared is easy. That's just 5 times 5. That's 25. And then now I need to use the power rule. So if I have p to the 4th squared, then remember the rule is I multiply the exponents, right? If I raise a power to a power, I multiply the exponents. So this is 8. And in the bottom, same thing. It'd be q. What would it be? It would be 10, right? So that would be my answer. 25 p to the 8th over q to the 10th. So this thing just simplifies to that. Okay, so the last thing I want to talk about in this section is a little bit on scientific notation. So let me get a new screen here. So scientific notation. The reason why we had to wait to talk about scientific notation is we need some of these exponent rules. Okay, so why do we use scientific notation? Well, typically it's used in science and engineering when you want to represent either really large numbers or really small numbers. Right? If you want to represent them more efficiently than writing them out in standard form. So it's used when you want to represent really large or really small numbers and you don't want to write them out in full in standard notation. So what does it mean for a number to be in scientific notation? Well, let me give you that first definition. So a number is in scientific notation if it is written in the form a times 10 to the n, where n is an integer, so where n, let me write that better, where n is an integer, so remember that's like 0, -1, -2, -3, 1, 2, 3, 4, right? Any integer could be 0. And a, and this is the important part, a is a number that is greater than or equal to 1, but less than 10. So the smallest that a can be is like 1.00000 and so on. The largest it can be is 9.9999. So a is always, if you write it as a decimal, it's going to have one digit and then the decimal point. That's what we mean by has to be greater than or equal to 1 and less than 10. It's always going to be some digit, so some digit, and then followed by a decimal point, and then the rest of the number. Okay, so it's easiest to learn this by example. Again, we're only going to do the very basics of scientific notation. So let's say I have a number written in scientific notation, and I want to write it in standard form. Okay, so let's say the number is 3.152 times 10 to the 4th. And so that's in scientific notation, right? So it's a number, 3.152, that's between 1 and 10, right? It's greater than or equal to 1, less than 10, times 10 raised to some power. In this case, the exponent is a positive 4. So the way I think about this is if you have a positive exponent, then this is going to represent a very large number, right? In fact, you can think of this as this really means 3.152 times, and then 10 to the 4th is 10 times 10 times 10 times 10. That's 1 with 4 zeros after it. So if you were to multiply that decimal value by 10,000, right, 1 with 4 zeros after it, that's equivalent to moving the decimal point 4 places to the right. So in standard form, this is going to be 31520. So the easiest way to think about this is the 4 here in the exponent is telling you to move that decimal point 4 places to the right. And since we don't have, we have to add a 0 there, right? So that's how I'm getting 31,520. If the exponent is negative, then it's the opposite. It really means it's a really small number. So, for example, if I have something like, say, 4.31 times 10 to negative 5, right? Really, this means 4.31 times, and then this would be 1 over 10 to the 5th, which is the same as 1 over 1 with 5 zeros, right? So 100,000. And that's equivalent to moving the decimal point 5 places to the left. So the easiest way to think about this is you start with your A, right? Your given decimal number. And then this negative 5 tells us to move the decimal place 5 places to the left. So this would be 1, 2, 3, 4, 5. So I have to put in 4 zeros there, so the decimal will end up there. And that would be my answer. So written in standard notation, this would be, you can always put a 0 in front. This would be 1, 2, 3, 4 zeros, and then 4, 3, 1. So that's this value, which is in scientific notation. This is the equivalent in standard notation. Okay, and of course we can always go the other way. So if I have, let's say I'm given a number in standard notation and I want to express it in scientific notation. So if I have, say, 2, 3, 2, 3, 4, and then say 5 zeros. So that is a really, really, really large number, right? So I know when I write it in scientific notation, I'm going to have a positive exponent on the 10. And the number part, right, the A part, has to be a number that's greater than or equal to 1 and less than 10. The other way of saying that is I need to put my decimal point between the 3 and the 2, right? I'd have to move this back. So originally the decimal point is at the end, right? So the whole number is right at the end. So I want to move it 1, 2, 3, 4, 5, 6, 7 places to the left. So this number now in scientific notation is going to be 2.34 times 10. And since I moved it 7 places to the left, this has got to be a positive 7. Okay. Another way of thinking about this is kind of a funny way to write the original number, but I could write it as 2, 3, 4, 0, 0, 0, 0, 0 times 10 to the 0, because remember 10 to the 0 is just 1, and if I multiply by 1 it's not going to change anything. And then you could just use the rule, well, if I have to move that decimal point 7 places to the left, then I want to add 7 to my exponent. But what's 0 plus 7? That's just positive 7. Okay, so if you write it this way, you can say, if I move the decimal point to the left, say, n places, then you're going to add n to the exponent. But since it's 10 to the 0, 0 plus 7 is just 7, right? So it's another way of getting 2.34 times 10 to the 7th. But you should also logically check it. Since you know it's a very large number, it's going to have a positive exponent. Okay, and of course, a small number is just the opposite, right? So if we have, let's say this is our original number. And I want to represent it in scientific notation. Okay, so where do I need to move the decimal? Well, I would need to move the decimal in between the 1 and the 3, right? Because I have to have a digit and then a decimal point, right? That's the only way I get a number that's greater than or equal to 1 and less than 10, right? Greater than or equal to 1 and less than or equal to 9.99999. It can't be any higher than 9.99999. So how do I get my decimal point from the original place to that position? Well, I'd have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So then this is going to be 1.3 times 10. And you can guess what the exponent has to be, right? It's a very small number, so we know it's negative. And we moved it 11 places, so this has got to be negative 11. Okay. The other way to think about it is what I did earlier. I could also think of this, okay, I can write this original number. And then I'll write in times 10 to the 0, right? Just because that's equal to 1. And then we can use sort of the general rule now, and I can say, well, if I move this 11 places to the right, so I move the decimal place 11 places to the right, then I have to subtract 11 from the exponents, right? So then you have the same idea as before. If we move to the left, we add to the exponent. If we move to the right, we subtract from the exponent. So if I move, I'll write the rule here. So if I move the decimal point to the right n places, then I subtract n from the exponent. So again, this would be 1.3 times 10. And then what's 0 minus 11? It's negative 11, right? And again, it's good to just to check it. Yeah, it's a very small number. I better have a negative exponent. So that makes sense. Okay, what if you want to multiply or divide numbers when they're in scientific notation and you want your resulting answer to also be in scientific notation? Let's do a few examples like that. Let's say I want to multiply 2 times 10 squared times 4 times 10 cubed. Okay. Well, really, when I say 2 times 10 squared, you can think of it as multiplication, right? It really is multiplication. And I'm multiplying by another number which has two factors that are multiplied together. And we know that when we multiply a bunch of things together, it doesn't matter the order in which we multiply. So I could rearrange these things, and I could think of this is the same as 2 times 4, right? Times 10 squared times 10 cubed. Well, 2 times 4, that's easy, that's 8. And then 10 squared times 10 cubed, we can use our rules. And we know that we keep the base, right? Because the bases are the same, so we keep the base 10. And what do we do with the exponents? This was the product rule. We add them, right? So 2 plus 3 is 5. So this would be 8 times 10 to the 5th, right? So really, you want to think of it this way. Multiply the numbers first. So 2 times 4 is 8. And then multiply, that'll give you the 8. Then multiply the powers, 10 squared times 10 cubed, and that gives you 10 to the 5th, right? And you do that by using the product rule. You have to add the exponents together. Okay, here's another one. What if I have 9.1 times 10 to the negative 13 times 6.3 times 10 to the negative 10? Okay, so the rule is, right, I multiply just the numbers first. So what's 9.1 times 6.3? You could do that out on your calculator if you want, right? You're going to get 57.33. Times, and now I do the powers, right? 10 to the negative 13 times 10 to the negative 10. Well, the rule is I keep the base, so 10 stays the same, and you have to add the exponents. Well, what's negative 13? What's negative 13 plus negative 10? This goes way back to chapter 1. It's negative 23, right? So this would be a negative 23. And now you might think, oh, I'm done. Okay, I have it in scientific notation. But this is not quite, right? It's not quite scientific notation. I need to adjust it a little bit because remember, I want my number, my A, that number that's out in front, it has to be a number between 1 or greater than equal to 1 and less than 10. So it has to be a single digit and then a decimal point. So I need to adjust this. I need to move this decimal point one place to the left because I really want it here between the 5 and the 7. But if I move that decimal point, I have to adjust the exponent here. So remember what happens if I move to the left, then I add, right, to the exponent. If I move to the right, I subtract. So if I move to the left, I add to the exponent. So this is going to be 5.733 plus, what's 10 to the negative 23 plus 1? I moved it 1 to the left, so I have to add 1. It's negative 22. So this would be the final answer in scientific notation. So make sure that this number out front, the A here, is a number that just has a digit and then a decimal point, right? It's greater than or equal to 1 and less than 10. So sometimes you have to do that. Sometimes you have to make that adjustment at the end there. Make sure it's actually in scientific notation. All right, what if we divide numbers that are in scientific notation? So let's say I have now 3.0 times 10 to the 4th divided by 1 times 10 cubed. Well, I could write this as 3.0 times 10 to the 4th over 1 times 10 cubed. Okay, so the first thing that you want to do is you want to divide the numbers out front. So what's 3 divided by 1? Well, that's just 3. Okay, times, so that gives me the 3 here. I just divide those numbers. Then I want to divide the powers, but we have a rule for that, right? The quotient rule. Remember, how do I divide powers? I keep the base, and then I would subtract the exponents. So 4 minus 3 is a positive 1. So that's how I'm getting the 10 to the 1 there. And that's my answer. So 3 times 10 to the 1 would be my answer in scientific notation. Okay, one more. Let's say I have 4.8 times 10 to the minus 3 divided by 8 times 10 squared. Okay, so again, I can write this as 4.8 times 10 to the minus 3 over 8 times 10 squared. And now I'm going to divide the numbers first. So I need to do 4.8 divided by 8. Well, if you work that out, that turns out to be 0.6. So 0.6. Right, that comes from dividing the numbers. And then times, now I have to do the powers. Well, how do I do the powers? Well, the rule is if I have the same base and I'm dividing them, I keep the base. So I keep the 10. And then I would subtract the exponent. So be careful here. Remember, this is like saying, I'll do it on the side here. Negative 3 minus 2 is a negative 5. So this is a negative 5. Now, are we done? Not quite, right? Because this isn't really scientific notation. I need to move that decimal point one place to the right so that it reads 6 point, right? The decimal point has to be after the 6. Remember, it has to be a digit, a number, and then a decimal point, or a number greater than or equal to 1 and less than 10. So to correct this, I'm going to move, let me write it down again here. I need to move this one place to the right, right? I need to move it right there. But then if I move the decimal place to the right, what do I do with the exponent up here? I subtract 1, right? Remember, if I move to the left, I add. If I move to the right, I subtract. So if I move one place to the right, I'm going to have 6 point, you can write a 0 there if you want, times. And if I subtract 1, well, negative 5 minus 1 is a negative 6. So this would be a negative 6. And that would be my result for that division. Okay, that's great. So that's all I wanted to do for scientific notation. We just wanted the basics of scientific notation. And you can see how it uses some of our rules for exponents. So the next section will be 5.3, right? I'll do that in a new video. I'll probably do 5.3 and 5.4. And there we're going to start talking about polynomials. So we'll define what a polynomial is, and then we'll start looking at rules for adding and subtracting polynomials, and then multiplying and dividing polynomials. All right, great. Thanks.